Hey everybody, Lars here. Time for the last review video for the course. This is Unit 6, and we're just going to do one review video for this particular unit. We're just going to go over some simple data structures. Stacks and queues, binary trees, linked lists. You've heard me tell the story before. This unit's about exposure. This unit is really about getting down to the nitty-gritty and working a lot. That said, you're going to have a couple assignments, and you're going to do some simple stuff with data structure. So I want you to be able to see things, and I want to go over some of the different tools you can use with Python in order to use these particular data structures. I always tell the story when I do these videos that I'll go back and I'll look in the past about the different times that I've done these particular topics, and I say, oh, that was good and that was bad, don't do that. No, that was good, and maybe not do that again. And every once in a while I run into a lecture that I like, and I'm like, ugh, I'll have to literally go through and copy the whole thing, and hopefully I do it right and this and that. And then you get to thinking, in this day and age and technology, well, just let them have that lecture. So that's what I'm going to do, in the name of saving a little bit of time, because it's the end of the semester and everybody's always jammed up, and getting some stuff done, and you getting a pretty good lecture on the topic. I'm going to go back and use one from the past. That said, after the lecture's done, stick around and we'll talk for a couple of minutes about the end of the course. But you're almost there. Data structures, final project, we're almost there at the end of the course, all right? So here's the lecture on data structures. Stick around at the end and we'll talk a little bit later, all right? All right, so let's go back in the past. What we're going to do is we're going to take a look at stacks and queues. I usually do them together. And if you remember from your slides, stack is nothing but a Pez dispenser. The first thing in is the last thing out. And you can see we have our little drawings there. So that's a fairly easy concept if you're familiar with Pez dispensers. It's just like a Pez dispenser. You push down, you push down, you push down, and then when you want to get one out, you pop it. That's it. Now the second closely related data structure to stacks is queues. Now queue is just what it looks like. It's like a line in the grocery store. When you go into the queue, it basically tells you what came before, what came after. It's used for scheduling purposes. And instead of the first thing in being the last thing out, now the first thing in is the first thing out. Okay, it's more fair, I guess, than you would think it would be with a stack. Stacks theoretically are more for remembering things, and queues are more for scheduling and keeping things in order. But let's do this. Let's look at some code. Load code. There we go. As you can see here, there's two things that we need to consider now that we're looking at data structures in our particular context. One is that we, thanks to beautiful Unit 5, know about object orientation. And object orientation lends itself nicely to these data structures. Because if you think about it, what is a stack? It's nothing but a list, but it's a list where we have different methods, push and pop, that do certain things with it. Now, the second consideration we have besides object orientation is that we're using Python. So Python has a lot of things already written for us that we can use. So when we deal with Python, and we're programmers that already know about object orientation, it's kind of neat because we can just use what Python gives us to implement what we want to implement. And as you can see here, I'm going to run it. And as you can see, let me put this right up here so we can take a look at it. At first, when I look at the stacks, and I will worry about this import statement in a second, but the first thing I'm going to do is I'm going to grab a variable called stack1, and I'm going to put a list in it. So then what do I do when I want to push to this stack or I want to add something to it? I just use the append method. Okay? Append is the same as push when we use a list as a stack. So I'm going to push the string test. I'm going to push the integer 2, and then I'm going to push the string test2. Then I'm going to come down here. I'm going to say print. First we look at stacks. And then I'm going to use a method called pop. And lists, you didn't learn about it when you learned about list. But if you go look in the online documentation, you'll see that list has a method called pop. And it's just what it is. It's so you can use lists as stacks. So if we go over here and we look at our results, we'll see first we look at stacks because we printed it. And then we're going to print stack1 pop. Well, what do we get? We get test2.
So test 2 was indeed the last thing we put in the stack. So if it's going to behave like a stack, the last thing we put in is going to be the first thing back out again, and that's what we get, test 2. Now if we pop it again, test 2 has been removed, and now we get the 2. So this is acting like a proper stack. Okay, now we look to queues, and a queue is just a line. We're not going to use a regular list when we do our queue, though. What we're going to do is we're going to go to the collections library, look it up online in the online Python documentation, and we're going to import a class called DQ, and we're going to get a DQ object. So I'm going to come down here, I'm going to get a value, I'm going to make it equal to DQ. We all know about object orientation right now, so DQ's constructor is going to get run, and I'm going to get that kind of object for my variable. And then I have two methods for DQ that let me treat it like a queue. One is append, just like our stack, the push to the queue, or usually when we deal with queues, we call it an insert. But in this case, we'll just call it append. I do the same thing as I did above, in the same order. String test, integer 2, string test 2. And then I start popping. But in this instance, I want to use the method pop left. So we come here now, we look at queues. I do a pop left because I want to grab the other side. I want to have this act like a line in the grocery store or a queue. So I don't use pop, I use pop left. And what do I get? I get test. So the first thing that went in is going to be the first thing that comes out now because I want the behavior to be that of a queue. I do pop left again, and it's the 2. It's the middle item, just like it was above. So what we have here is we have one is a stack data structure, and the stack data structure is so we can basically use it as memory. It's like I'm in the middle of doing something and you go, oh, I have to go do something else. So you push that thing to the stack, then you do what you have to do, then you pop it again so you can get it right back. It's almost like it acts as memory for small tasks. It's like, oh, I have to do this. Well, all right, I have to do this now. Push it, and then push this, and then, okay, I'm done. Pop it. Do that. Pop it again. Do that. That's how we use stacks in a computer science context. Queues are for, quite simply, scheduling, because it seems simple, but what do queues really tell you? It tells me what went in before me. It tells me what went in after me. And even though I don't have to keep a specific time, I do have that, temporal sense of things that are coming before and after me. So in computer science, we use it for scheduling. So stacks and queues are used throughout programming and computer science all the time. So it's definitely two data structures that you want to be familiar with and you want to have at least, heard about. Okay, so that's pretty much the meat and bones of stacks and queues. In your slides, we then go on to talk about binary trees, but I think I'm going to say binary trees for last, because what I really want to do in this particular video / demonstration is I want to give you the skinny on linked lists. Nah, I don't need this anymore. Get rid of it. But what I'm going to do first is I'm going to do a drawing, and hopefully I can do the drawing well. When we have a linked list, the first thing we do is we introduce you to the concept of, I'm trying very hard to do this well, a node, okay? And a node is an item in a list, but it's not just one single piece of data. It's two pieces of data. In here, you have your data, and in here, you have a memory location that points to the next item in the list. Because this is the secret. Back when we got used to storing things, you had memory where everything was all in a row. So the first item in the list would go here in the 0 spot. And the next item in the list would go here in the 1 spot. The next item here would go here in the 2 spot. And so on and so on and so on. The problem is, to use memory well, sometimes you don't have your memory all in a row, or what's called contiguous. Sometimes you want to jump all over and use memory where you can find it. Let me get rid of this. So a linked list allows us to do that, because a linked list allows us to do what we call dynamic allocation. If I have a list and it's 2 items long, if I want to add that third item, all I have to do is go grab a piece of memory from anywhere, because this pointer allows me to point to it. Now, I have a node, which is the data item or the payload, and then a little spot that points to the next item, but that's just a node. What I really want is I want an object called a linked list, and what the linked list is going to handle is two different things. The linked list is going to tell me, watch the spelling on this. Oh boy, that's bad. Look at that, I fixed it. There's an item called head, and what head does is it points to the first item in the list. And then the second thing a linked list keeps track of is what the size of the list is, and you'll see this gets handy later too. Okay, so if I have a linked list, it points to the head. So my linked list is going to point to the first item in my list. This is a node. So what is this going to do? If there's only one item, it's not going to point to anything. It's going to have what's called a null pointer, or it's going to be 0. But if you do have a second item, let's say I have an item out over here, well then this is going to point to it. Okay? And then I have my second item here, and then this will point to the third item in my list, and so on and so on. Now the last item in the list is going to have, I'll just put an N there for null. That is a really weak N. Let's try that again. A little bit better. Oh, look, a little mark at the end too. How wonderful. So this is basically what a linked list looks like. And every time you insert something or add something to the end of the linked list, you would update your size variable. That would be basically a class variable. You learned about class variables in Unit 5. Okay? So that's for this simple context and for the simple thing we're looking at right here. This is what a linked list is. In a data structures course, hopefully, you know, I know there's that course in Camden where you can do data structures and algorithms, and I'm sure they go over this there. You could spend a month tooling around with linked lists, because what you'll learn later is this is what's called a singly linked list. If you had a doubly linked list, your node would have 3 items. You'd have your data or your payload. You would have a pointer to the next item, but you would also have a pointer that it would allow you to go backwards. That would allow you to go to the one before. And that's called a doubly linked list. So with a doubly linked list, you can go to the end of the list and go all the way back. Here with this singly linked list, you can't really go backwards. Okay? And then what you would do is you would write different methods for your linked list object. You would have one called insert. So if I want to insert an item in the third spot, what would I do? I would come here, I would take my new node, and I would have the pointer point to this one, and I would take this one and break that and have it point to this. So I would be inserting that item in the third spot. Okay? That's messy, so we'll get rid of that. I could also write a delete. A delete is incredibly simple with a linked list, because let's say I wanted to delete the second item. All I have to do is break this pointer and take this and point to this. That's it. That's a delete. Because now this guy, he still exists, but he's out in space. When I look at the linked list, this is my first item, and it goes to the second item. So that's it. Okay? So that's basically what a linked list is. It's a list in non-contiguous memory, where your list item is a node that contains your payload or your data, and then just a pointer that points to the next item in the list. Okay? So if we want to implement this in code, I will come back to this later. Let's see. I have a linked list, little piece of code called a linked list, but I also have a little piece of code that uses it. And if you look here, and you have this online because you're going to use this with your homework, I don't have one class here. I have 2 classes. I have node, okay, which contains data, and the next node. So I basically have what my payload is, and then I point to the next thing in the item. So that's my node. I have my payload. One thing is the payload. One thing is what the next thing is. Here it's a variable name. It's not a pointer to a memory location. And then I have my linked list. What does my linked list do? The 2 things we said it would do. It keeps track of the head, it keeps track of where the top of the list is, and it has a variable to maintain the size. And size is 0 right now. This is actually an instance variable. I didn't use it as a class variable like I said before. So what are my methods? My method's an insert. So I say insert a node. So if not the head, because if it's the head, we want to do something a little different, then make self.head equal to node. So basically what I'm doing is I'm kind of treating my object-oriented linked list as a stack, because I'm pushing the object down and creating a new head every time I add something. And you're going to see when we run it. And then I'm increasing the size. Now, if it is the head, then we have to do a bunch of other stuff down here. Okay? If I want to get the size, I have a getter for my size variable, which is increased in both cases. And here I put in a little print so we can print it. Okay? So when I use my list over here, I created a library, because that's what we do, and I import everything from the linked list library. I grab a variable called myList, and I make it equal to linked list, and then I start inserting things. So what do I insert? I insert nodes, okay, because that's what linked lists have, nodes. All right. You can see up here, I don't call it a node, I call it an object. So my class accepts an object when it's created. So although I didn't do it here. So when I do my insert, which takes a node as a parameter, I give it a node. I give it Lars, okay? And then I give it Alex. And then I look to get the size. Let me run it. Show you. Ooh, let me get in here. Okay, so what's going on down here? You can see when I run it, what do? I insert Lars, then I insert Alex. Then I do a get size. What's the get size 2? Then I insert Michael. Then I do a get size. What's the get size 3? Then I insert Abby. These names, these are all names of students that I had a couple of years ago when I used to teach Python to middle school kids in an enrichment program at an enrichment school called Heroes Academy in New Brunswick. So I kept all their names here. So these names aren't coming out of the blue. They were actually students that I had a long time ago. Good kids too, smart kids. Then what do? I come down here. Oh, don't want to do that. And I use the print LL function. So I print my linked list. And what do I do here? I just start at the front node and I go through node and I keep printing until I run out of data. And so that's what I do here. But you'll notice the order. Abby, Michael, Alex, Lars. What do you notice about that order? It's like a stack. Okay, Abby was the last thing we put in, but it's the first thing out. So this linked list is like a stack. Okay. So when you're inserting things, you've got to remember whatever you insert is going to be the head of the list. All right, and that's going to help us out. Now, one thing that we have is I gave you a homework assignment. And that homework assignment was to write a method for linked list. So when you write a method for linked list, you would put it in here with the linked list code that prints a certain item in the linked list. Okay, so if I have this list right here, Lars, Alex, Michael, Abby, and I want you to print the second item, I want you to print Michael, because Michael is the second thing in the list. Now, you're probably thinking, oh my God, how do I do that? I'm not going to do your homework for you, obviously, but I can do something that may make things a little interesting for you. Let's go down here to the print LL method, okay? And let's just add a counter. Simple counter. Yeah, do that. And now when I print the data, I'm not just going to print the data, I'm also going to print the counter. All right, so let's do that. Let's save that, run it. Nothing's going to happen because it's a library. But now if I come back here and I run my code again, now I get the number that it's put in. Aha, see? So that may help you down the line as far as your homework is concerned. Yes. All right, so that's basically it as far as a linked list is concerned. It's not a difficult concept. It's just I don't have all the memory right in a row to store what I need to store. So I'm going to create a structure where I have an item in a list and it points to another place and that points to another place. So I can now logically have a list of items, whereas physically they are not right in a row with each other. Okay, and that's all a linked list is. As you probably know already, this code is already up on the Sakai resource site for you to use. So you can use this code, take it, and then just add the different functions you have to add in order to do your homework. But if you play around with this code and you trace it and you understand how it works, you're going to understand linked lists. And the two homework items that you have shouldn't be that difficult once you have that context and that understanding, okay? One last thing we're going to do, and I'm not even going to look at code with it, is we're just going to review binary trees. And what do I want to do here? Let's go new. Don't save. Yes, brand new. And we're going to look at binary trees. Now, I already told you about the concept of a node. So it's pretty much the same thing with binary trees, except here I'm going to have data or a payload in the middle. And then I'm going to have one side point to the left-hand side, or what we call a left leaf. And then this side is going to point to the right-hand side, or what we call a right leaf. And that's what a node looks like in a binary tree context. But when you see binary trees drawn, you usually see something like this. Okay? Each one of these circles is a node, just like that. Okay? So you'll have this node up in the middle, and this node points to another tree structure, and then this node here only has a left leaf, and it points to this. Oh, no, I mean this one only has a left leaf and only points to this, and this one has both, but this one only has a right leaf. And you're probably saying to yourself, why in God's name am I storing my data in this fashion? And part of the reason, as you'll understand if you take a data structures course or you start moving on in computer science, is that this kind of structure lends itself to being attacked recursively. Because if you think about it, I have a binary tree node up here. What do I have at either leaf? Another binary tree. Okay, what do I have here? Two more binary trees. This is a binary tree. So if I have a recursive function and I run it here, I say, get right. Do I have a right leaf? Yes. Do I have a right leaf? Yes. Do I have a right leaf? Yes. So it's basically, okay, is this still right? Run yourself again. Is this still right? Run yourself again. Is this right? Run yourself again. So it leads itself to recursion. Then is this right? No. Well, that's your tail condition. That's your end condition. Oh, really? No. So then I go up the leaf. And then I can check for lefts as I go and do other things like that. As you saw in your slides, there's different orders through binary trees: infix, postfix, prefix. So you can basically traverse and store data in a bunch of different ways. You'll see later, if you take that data structures course, that binary tree structures are very good for sorting and searching. It allows us to find data really quick if things are stored in a binary tree structure. And you already got a little hint to some of that when we did binary searching in Unit 4. So this is all what binary trees are about. This, when you see something like this, that's what it is. It's a binary tree. And all it is a node where the data is here, and these two are pointers to what's off to the left and what's off to the right. And what's off and off to the left and off to the right is another binary tree. So we run recursive methods and recursive functions on this particular structure. Okay? Not going to make you crazy with code on this one. As you move forward in your data analysis, big data, data science / computer science careers, you are going to run into binary trees a lot. So you are definitely going to see some code and see some stuff on binary trees. And you could always Google it and look at it that way too. But for brevity and for time's sake, we are not going to do that here. All right? That's it.
All right, we're back. I just wanted to come back and say that all of these resources, the videos, the slides, the discussions, everything that you have up in Canvas is going to remain up in Canvas so that you're going to be able to go back and use these as resources. You can, anytime you wanted to go rewatch a video, you know they're all up on YouTube. You know where they are. I leave the slides where they are. So I hope you have the Zell book in your library going forward. That's why I wanted you to have it. But also I want you to realize that the slides and the videos that we've gone through will also be part of your resources going forward as now you're Python programmers. So if you ever want to brush up on things, you know, go back in the past and look at how things worked, you'll be able to do that. Okay? But other than that, we're done as far as the videos are concerned. All right? I hope you enjoyed it. I hope you had a good time and had a good experience going through a programming course this particular way in a hybrid format. All right? Good luck on everything going forward. If you're graduating, congratulations. Other than that, you be good, and I'll see you around. All right? I'll talk to you later. Bye.